In this lecture, we'll be studying about FM modulation, commonly known as frequency modulation technique. The frequency modulation technique is the frequency of a carrier wave is varied in accordance with the instantaneous amplitude of the message signal. So consider this is a message signal which is of low frequency and the peak value of that signal is EM. This is a carrier signal whose peak value is EC and it is of high frequency. A final modulated signal will contain the same amplitude as that of the carrier signal called EC and its frequency is going to vary. So let's see how the frequency is going to vary. When the message signal's amplitude is going to increase, the frequency of this wave will also increase. When it reaches the peak value, it will have the highest frequency. When the amplitude reduces, the frequency of the modulated signal will also reduce. Now let us derive the expression for FM wave. Let the message signal be represented by small letter em is equal to capital EM into sine omega t. So here, since it is a message signal, it has been represented by small letter em, where m stands for the message signal. E is the instantaneous value of that signal. Capital EM represents the peak value of that signal and this represents the frequency and the phase part. The carrier signal can be represented in a similar way. EC, which is the instantaneous value, capital EC, which is the peak value, and this is the phase and the frequency part. Now the resultant frequency modulated signal can be represented by F, which is equal to Fc, where Fc is the frequency of the carrier wave. It is this frequency that which is going to vary and it is varying in terms of this. That is K, which is a proportionality constant, and it is going to vary with the amplitude, instantaneous amplitude of the message signal, and the instantaneous amplitude of the message signal is given by this value, that is Em sine omega mt. That we are going to multiply it with a proportionality constant and we are going to add it with the carrier frequency. Any signal can be represented as small letter e is equal to capital letter A into sine theta, where A is the maximum value. So here the instantaneous magnitude of the FM signal is given by EFM, which shows FM modulated signal, and A is the amplitude, then sine phi. So phi is the phase of that signal and we know that phi is equal to integral omega dt, where omega is the angular frequency. So this omega can be represented as omega c into 1 plus k em sine omega mt into dt, which we have seen in the previous slide. That is, instead of f over there, we are going to just replace it with the angular frequency omega. So instead of omega, we'll write it as omega c 1 plus k, which is the proportionality constant, and em sine omega mt, which is the amplitude of the message signal. Now let us integrate this term. So omega c into 1, we are going to integrate with respect to t. So we'll get it as omega c t minus k is a constant, em is a constant. Sine omega mt, when integrated, we'll get it as minus cos omega mt by omega m. And again this is multiplied by the term omega c. So we'll get this term like this. And instead of omega c and omega m, we're going to write it as 2 pi fc and 2 pi fm. So 2 pi and 2 pi will get cancelled. So it will become ordinary frequency terms fc and fm instead of the angular frequency terms. Now this entire term, that is k em fc by fm, we are going to write it as mf for the term of simplicity, and this mf is called as the modulation index of fm. The numerator term k em fc is also called as frequency deviation and it can be represented by delta. So the final expression for an FM modulated wave, which we found in the previous slide, is EFM is equal to A sin phi, where A is the maximum amplitude. So instead of phi, we are going to replace it with this expression that we found out by integration. So we'll get it as omega CT minus MF, where MF is the modulation index of FM, into cos omega MT. Now here you can see that this is a function of a function, that is sine of cos. So it can be only expanded using a function called as Bessel's function, and it will become a very complicated expression. So we have to learn only till here, that is, this is our final expression as of now. Now let us study the advantages of FM when compared to AM. We saw that in AM there is also a carrier term, that is, there are three terms: LSB, carrier and USB. So a certain amount of power is dedicated to the carrier and the main information lies in the LSB and USB. So some amount of power is wasted in AM, whereas for FM the entire transmitted power is useful. Next, FM is more immune to noise when compared to AM. Then also FM has a guard band between adjacent channels so that interference will be very less. The amplitude of FM is always a constant, that is, it remains that of the carrier wave and hence it is independent of modulation index. In AM it depends upon the modulation index. Therefore, a small power is required to produce 100% modulation index for FM, whereas a large amount of power has to be dedicated to bring in modulation for AM. Next is the disadvantages of FM or the advantages of AM. FM has a bandwidth which consists of infinite sidebands, but in AM there are only two sidebands, LSB and USB, so a small channel is only required, whereas for FM we need a wider channel in order to transmit the message. Secondly, the transmitter and receiver of FM is very complicated and hence the cost of that equipments will be very large when compared to AM. And finally, since the reception is limited to the line of sight, the area covered by FM will be much smaller than AM. That is, only a small area can be covered by transmitting an FM signal.